Hi everyone. We are going to present about comparative analysis of blockchain consensus algorithms, and we are group 3, and these are the group members. Our focus today is on how different blockchain systems ensure all participants in the network can agree on the same data even when they don't fully trust each other. So, this process is called consensus and it plays a crucial role in making blockchain technology secure, decentralized, and reliable. Instead of having a central authority to verify transactions, blockchain relies on consensus algorithms to keep the system honest and synchronized. In this presentation, we aim to explore the key challenges involved in reaching consensus across distributed system, and we'll also compare the different algorithms developed to solve this problem, looking at strength limitations and real world applications. Let's move to next slide. Now, to begin, let me introduce the research paper that our presentation is based on. This was written by L.M. Back, B. Mihajevic, and M. Zagar from the Rochester Institute of Technology in Croatia, and it was presented at the MyPro 2018 conference held in Optija, Croatia. As of October 2023, the paper has been cited over 160 times and showing that it has made a meaningful contribution to ongoing blockchain research. It offers a detailed comparison of several major consensus algorithms and evaluates them based on performance, scalability, and resilience. This paper is especially useful because it not only breaks down the theoretical aspects of consensus mechanisms but also discuss their practical implementations in real world blockchain systems. Let's move to next slide. Before we look at these algorithms, let's talk about the core problem they solve, reaching consensus in distributed network. In blockchain, all participants or all nodes must agree on single correct version of the ledger, but this is not a simple task. Nodes may be located in different parts of the world. The communication between them might delayed or faulty. In some cases, certain nodes may act even dishonesty or try to disrupt the system. So this challenge is best explained through the classic Byzantine generals problem. Imagine uh, a group of generals surrounding a city who must all agree on whether to attack or retreat. However, some generals might be traitors trying to confuse the others. They send misleading messages or withhold information. So, in this concept context of blockchain consensus algorithm, the answer to this problem, they are designed to help honest nodes reach a common decision, even if some nodes are faulty or malicious. To continue the presentation from the research methodology, I would like to invite Nuran.
Thanks, Kalangi. So, how did the authors go about their analysis? Their methodology was broken down into three clear steps. First, for selection criteria, they focused on the algorithms used by the top 10 cryptocurrencies by market capitalization as of early 2018. This wasn't just a theoretical exercise, it provided a practical look at the algorithms that were actually being used in the real world. Second, they established a comparative framework based on three key metrics: scalability, security, and energy efficiency. Scalability here refers to the number of transactions per second the network can handle, and security, specifically how resistant it is to an attack. Finally, for data sourcing, they gathered information from a mix of academic white papers, official documentation, and in some cases, community and third party sources. Next slide, please. With that framework in mind, let's look at the algorithms themselves. The two most famous ones are proof of work and proof of stake. Proof of work, or POW, is the original, and it is what's used in Bitcoin. Miners around the world compete to solve a very difficult computational puzzle. The first one to solve it gets to add the new block to the chain and is rewarded. The major pro here is that it's extremely secure. However, it's also incredibly slow and consumes a massive amount of energy. To solve these issues, proof of stake or POS was created. Instead of, instead of competing with computing power, validators are chosen to create blocks based on the amount of cryptocurrency they hold and are willing to stake as collateral. If they act dishonestly, they lose their stake. This means it's far more energy efficient and scalable. The main potential downside is that it could lead to wealth centralization, where the richest stakeholders have the most control. Next slide, please. Building on these core ideas, we have several important variants. Delegated proof of stake or DPoS, which is used by EOS and is designed for speed. Instead of everyone being able to produce blocks, stakeholders vote for a small fixed number of witnesses who do the work. This makes the network much faster and more scalable. Delegated Byzantine fault tolerance or DBFT, which is used by NEO, is also similar. Token holders elect bookkeepers who must reach a supermajority consensus, which is over 66%, to validate a block. This allows for very high throughput and, importantly, single block finality, meaning a transaction is permanent once it's in a block. Finally, we have RPCA, Ripple Protocol. It's different altogether. It relies on a list of pre-approved trusted nodes to achieve rapid consensus. This makes it extremely fast, but it comes at a cost of being more centralized than the other systems. Now, Gipme will take us through the paper's key findings, starting with scalability.
Thank you, Nuran. If we consider about the scalability, the study shows a wide range in transactions per second. We can see that Bitcoin handles about 7 transactions per second, Ethereum around 15, Ripple can handle 1,500, Stellar up to thousands, and EOS claims millions. For context, PayPal handles around 193 transactions per second, while Visa can do up to 24,000. So this highlights how far traditional POW systems lag behind in scalability. If we move on to the next slide, we can see the security differences. And here you can witness that the security differences, they depend on the algorithm type. For example, in POW, the attackers must control over 50% of the network's computing power in order to gain the power. And for POS and DPoS, the attackers must control more than 50% of the staked coins. If we consider the BFT models, they can tolerate up to 33% of malicious nodes. So the cost and nature of an attack vary significantly between these models. And if we move on to the next slide, here we can see the energy cost of POW. One of the most striking findings in the paper is the enormous energy consumption of proof of work algorithms. In 2018, the Bitcoin network alone consumed over 50 terawatt hours of electricity annually. That's more than countries like Portugal, Singapore, and Croatia consumed in the same year. To understand this better, 1 terawatt hour is a huge amount of energy, and it is enough to power millions of homes. In Ethereum, which also used POW at that time, consumed more than 14 terawatt hours annually, which is comparable to the total consumption of a small country like Slovenia. These high energy demands arise because POW requires miners to continuously run powerful computers to solve complex puzzles. This process is extremely computationally intensive, leading to high electricity use. As a result, POW has faced criticism for its environmental impact, particularly in regions where electricity is generated from fossil fuels. Now I would like to invite Sahan to move ahead.
Thank you, Geetji. Uh, Here are the key takeaways of this comparative analysis. As we conclude this comparative analysis of blockchain consensus algorithms, it's clear that no single algorithm is universal solution. Each has its own strengths and weaknesses, whether we are dealing with cryptocurrencies like Bitcoin and Ethereum or enterprise applications. The choice of consensus mechanism requires balancing security, scalability, and energy consumption. Increasingly, the developers are trying to turn into hybrid and customized applications to their specific needs. A major conclusion is the ongoing trade-off between security and scalability. Proof of work, as used in Bitcoin, remains extremely secure due to the computational effort needed for attacks. However, it sacrifices scalability and consumes a massive amount of electricity. In contrast, proof of stake and delegated proof of stake boost scalability but can introduce risks like centralization of power. Meanwhile, algorithms like PBFT or its variants, Ripple and Stellar, deliver speed and efficiency, but typically work best in permission, less decentralized settings. Each model has also responds differently to threats. While proof of work is vulnerable to 20% attacks, BFT systems might handle faulty nodes, malicious nodes. Another key point is block finality and transaction performance. Proof of work systems provide only probabilistic finality, meaning that transactions are more likely to be permanent the more blocks are added. But there's always some risk of reorganization. BFT style protocols used in many enterprise settings offer instant deterministic finality. Once a block is confirmed, it can't be reverted. This is especially valuable for financial or legal applications. In terms of speed, proof of work blockchains like Bitcoin and Ethereum process a handful of transactions per second, while POS and DFT based blockchains can reach hundreds or even thousands of transactions per second. The difference in energy use is also staggering. Proof of work blockchains can use as much electricity as small countries, while POS and DFT models are far more efficient. Environmental concerns have become a driving force in the shift away from proof of work. Many organizations are moving towards the proof of stake, delegated proof of stakes, and Byzantine fault tolerance based permission blockchain, which not only lower costs but also enable regulatory compliance and high performance. This makes them particularly attractive to businesses and government applications where efficiency, control, and sustainability are essential. Looking forward, the trend toward the hybrid and adaptive consensus mechanisms that blend the security of proof of work and the efficiency of proof of stake and the rapid finality of proof BFT. There's a growing focus on quantum resistance and privacy, especially as blockchain technology moves into areas like IoT and finance. As adoption spreads and new cases emerge, consensus algorithms will continue to evolve, striving to deliver the right balance of speed, security, and environmental responsibility. Thank you. This is the end of our presentation.